Hello everybody! In this video, we're going to learn how to do calculations with parametric equations of lines. In the previous video, you learned how, given 2 points, either in 2 dimensions or 3 dimensions, how to find the parametric equation of the line between those 2 points. And we wrote it in this form: L of t equals a slope vector m times your parameter variable t, think of that as time, plus a base point on the line. Now that we know how to derive equations of lines, now we can do calculations with them. And these fall into 2 main categories depending on the information you're given. And also, each of these questions, depending on the answer, might have some extra bonus sub-questions you can look into. The first situation happens when you're given a point and a line. The most natural question to ask is the point on the line? If so, cool, you're done. But if not, hey, that's even better because you get to do more math. In that case, you can find the closest point on the line to your given point, and then find the distance between your original point and that closest point. And so we can ask those 2 questions if you're given a point and a line. Alternatively, if you're given 2 lines, you can ask the question, do those lines intersect? In 2 dimensions, this isn't a very interesting question because really you only have 2 cases. Either your lines are parallel or they intersect. But in 3 dimensions, it's a lot more interesting. You might have lines which are not parallel but also don't intersect. Those are sometimes called skew lines. So, there's 2 possibilities. If the lines do intersect, you will naturally want to figure out at what point they intersect. If they don't intersect, you could ask, what's the distance between those lines? Kind of similar to the question, if a point's not on a line, what's the distance between them? All right, let's jump in and do some math. So first, to answer the first question, let's assume that you're given a point A and the equation of a line L of t. If it is possible to find a single value of t where L of t is equal to A, then the point A is on the line L. And I like to think of t as the time as you move along that line. So if at some time you reach the point A, then the point A must be on the line L. So here's an example. Let's say L of t is the line with slope vector 2, 1, 3 times t plus base point 3, 1, 1. Now last time we talked about we were able to take this parametric vector form of this equation. We could actually break it down into 3 equations, one for each of the parts x, y, and z. For instance, the x value is given by the first components, so x is equal to 2 times t plus 3. The y component is equal to the second components here, 1 times t plus 1. And the z component is the third parts, 3 times t plus 1. And so we could change that equation into these 3 separate equations. And this is really good to answer this kind of question, because if you're given a point A, then you're given some values for x, y, and z. You can plug those in and then see if you can get a consistent value for t. For example, using this equation of a line, is this point 13, 6, 16 on the line? Well, to figure that out, put in the values 13, 6, and 16 in for x, y, and z, and solve each of these equations for t. Right, there's 3 equations, but they're all pretty simple equations. When you solve them, in this example, you'll find that in each case, t is equal to 5. Since you're able to find a single value of t, at that time t equals 5, the line passes through this point? The answer to the question is yes. For a second example, what about the point 7, 3, 4? Is that on the line L? Well, you follow the same procedure. Plug 7, 3, and 4 in for x, y, and z, that set of equations. And when you try to solve for t, you will be able to solve for t in each line, but you don't get a consistent answer. In this case, when you solve the x and y equations, you find in both cases t is equal to 2. That seems promising. However, when you solve the z equation, you find t is equal to 1. So this line passes close to this point, right? So when time t equals 2, you do pass through 7 and 3, but when the time is 2, you don't satisfy this value here, right? You realize by solving this that you passed through this z coordinate at an earlier time, right? So there's no time at which all three of these values are on the line at the same time. So the answer to that question is no. And that's how you find out if a point is on a line. So one more example. This one's even more fun because you get to do even more math. Is the point 5, 7, 4 on the line from the point 0, 1, 0 to the point 1, 2, 2? Now in this case, you're not given an equation of a line, so we have to figure that out first before we go forth and determine if the point's on the line. Now, the equation of the line from this point to this point, this is a nice review of what we did before. We could figure out the slope vector by subtracting the first point from the second point. So the line is 1, 1, 2 times t plus a base point. I'll use 0, 1, 0. That makes the algebra easier. Once you have the equation of the line, you can break it into 3 equations for the x, y, and z parts. So x is 1 times t plus 0. Y is 1 times t plus 1. And z is 2 times t plus 0. Set those equal to the components of your point, 5, 7, 4. When you start solving these, the first equation, as soon as you simplify it, you get the answer for t. It's t equals 5. The second equation, you get t equals 6. And already at this point, you can stop. There is not a consistent value. It doesn't matter what the t value is for z. Already, x and y disagree. So in this case, the answer is once again no, this point is not on this line. However, don't despair, we can still do more fun math when the point is not on the line. In this case, we can calculate the distance from the point to the line. So here's the situation that we have. Let's say we have a line L with this equation. So we know there's a base point P on the line and a vector M that points along the direction of the line. And we have some point A, which I've drawn up here. And A is not on the line L. We'd like to do 2 things. We'd like to find the distance from the point to the line, right? The first step, we could find the closest point on the line L to the line A. And that closest point, we know it's the closest point if the line connecting A to B is a perpendicular line. Right? If we draw a line from A to any other point, such as P, if that line's not perpendicular, then that line is not as short as possible. When we're looking for the distance from a point to a line, we really implicitly mean the shortest distance, the length of this perpendicular segment. So to find this closest point B, it's not too bad. It incorporates a lot of things we've learned up to this point. We can break it down into 3 steps. The first step will be to find the vector from P to A. I'll call that vector V. We can calculate that as A minus P. Next, we'll calculate the projection of this vector V onto the line. But projecting it onto this line is the same thing as projecting it onto this slope vector. So we'll calculate the projection of the vector v onto the vector m. We'll call that vector p for projection. Not to be confused with p for point. The projection vector has a vector symbol above it. Finally, once we have this projection vector, right, it goes from p all the way down to the perpendicular. Right? We learned about projection vectors before. That's the defining characteristic of them. Once you have the projection vector, start with your base point, add the projection vector, and it translates you exactly to this base point B, from the base point P to this closest point B. So B can be calculated as P plus vector P, the base point P plus the projection vector. Once you've got B, calculating the distance is relatively straightforward. First, we need the vector between these 2 points, and it doesn't matter if it's A minus B or B minus A. It doesn't matter which direction that vector points in, because we're really interested in the distance between those 2 points, which is the length of this vector. And that's how we can answer our other questions, right? Finding the closest point, B, and finding the distance from the point to the line, that's this right here. As an added bonus, there's a nice way to check your answer. In this case, notice that we also have a right triangle. Right triangles are our friends in mathematics because we can use the Pythagorean theorem to solve them. In this case, the hypotenuse is this vector v, so we could find the length of the hypotenuse by calculating the length of the vector v. This side of the triangle, which lies along the line, that is the component of the vector v onto the vector m. So we can calculate the length of that side. But once you have the lengths of 2 sides of a right triangle, you can use the Pythagorean theorem to find the length of the third side. Right, so in this case, we'd know that c squared, in this case c is this side of the triangle, it's not the hypotenuse. C squared, the component squared, plus this distance squared is equal to the length of v squared. Then you could rearrange that equation, solve for the distance, life is good. All right, let's do the calculation. Lots of numbers. There's virtually a wall of numbers here. Don't worry, it's because they're fractions. It looks worse than it really is. Just remember to take it step by step. So previously, we learned that the point 734 is not on this line, L of t. So always keep this diagram in mind. The first step is to calculate this vector v. We calculate that as the point A minus the point P. And we'll find after doing the subtraction, you get the vector 4, 2, 3. Next step is to calculate this projection vector, projecting vector v onto slope vector m. And this is the projection formula, which we covered in a previous video. V dot m divided by m dot m, that'll give you a fraction that you're going to multiply times the vector m. In this case, you get 19 over 14 times the vector 2, 1, 3. And you can simplify some of the fractions if you want. That might make your life easier. So here we get the projection vector. Finally, to get this closest point, you're going to take your base point, 3, 1, 1, plus this projection vector, 19 over 7, 19 over 14, 57 over 14. You're going to need to do some common denominators. But when you're done, hey, you get this base point. Now, this should probably be written with parentheses, since I'm thinking of it as a point rather than a vector. But that's your closest point, right there. Very nice. Once you have the closest point, you can calculate the distance between these 2 points. First, find the vector between them. Again, for the mathematics to work out, I'm going to do some common denominators. So take the point A, get the denominators I need, so A is equal to this. Do the subtraction, either A minus B or B minus A. In this case, I did A minus B. Right, and here's the vector W. That's a vector between these 2 points. And then the length of that vector, in this case, you're going to do the square root of the first part squared plus the second part squared plus the third part squared. Get everything over a common denominator. You get the square root of 630 over 196. Amazingly, somehow, these actually have a common factor of 14. So you can simplify this. It's the square root of 45 over 14. Normally, I wouldn't be too concerned with simplifying something, right? This is a perfectly correct answer. But since I'm going to want to check it, it'll help to simplify it. And I know that there's a lot of numbers here. I've spared you all the arithmetic steps. But if you want, I know I'm going pretty quickly through this. Feel free to pause the video at any point, write down some numbers, check the calculations to make sure you can do them. And then once you're done calculating the distance, again, the check is to use the Pythagorean theorem. The length of this vector v is the square root of 29. The component is the length of this side. Right? The formula for the component is v dot m divided by length of m. In this case, that's 19 over the square root of 14. And this should look familiar. Because remember, the component is closely related to the projection vector. And this fraction we see here looks very similar to this fraction, except the component has that square root in the denominator. Once you've got these two numbers, set up the Pythagorean theorem, like so, and you want to solve for the distance. So you're going to square these. You'll need to do some work with common denominators. But once you're all done, you'll find that the distance is, once again, the square root of 45 over 14, because mathematics is consistent. And if these two numbers aren't the same, then I'm sorry to say there's probably an arithmetic mistake, and you'll need to go back through and check it. But at least you'll know. As a second example, this example is a little bit nicer because the numbers are a little bit easier to deal with. We previously learned that the point 574 is not on this line with equation 112 times t plus 010. So, same steps as before. I'm not going to bore you too much by reading through all the vectors, but just want you to become familiar with the process. So calculate the vector v from P to A. Calculate the projection of the vector v onto the vector m. Here's our projection formula. And then this isn't too bad. These are all denominators of 6. In theory, you could reduce that, right? Because these are both even numbers in this last component. But later on, we're going to need to recombine these fractions anyway. So in this case, I just left it as the 6. Well, once you've got your projection vector, to find your closest point, you add your base point plus the projection vector. And here you go, that's your closest point. Define this distance from point to line. Find the vector between your original given point A and this new closest point B. And here's the vector between those 2 points. An A minus B or B minus A, either way is good. Calculate the length of this vector, and that gives you the distance between these 2 points. In this case, it's the square root of 606 divided by 36, which, again, nicely simplifies to the square root of 101 over 6. To check that, we use the Pythagorean theorem combined with components. So, we have the hypotenuse is the length of v, which is square root of 77. This side of the triangle is the component of v onto m. That works out to be 19 over the square root of 6. Set up your Pythagorean theorem, solve for your distance, and you'll end up, once again, with a square root of 101 over 6. Again, math is consistent. Now, the other big question we're interested in, instead of starting with a point in a line, what if you start with the equations of 2 lines? In this case, a natural question to ask would be, do those 2 lines intersect? So here I have a diagram, and I have a line L and a line K. maybe I should have put an XYZ axis in here. Think of these as lines in three-dimensional space. Right? So maybe this line A lies above the line K. Maybe this isn't a real intersection, or maybe it is. That's what we're trying to figure out. So I have a line L and a line K. Each of those lines has a base point. Each one has a slope vector. The question is, does a point A of intersection exist? Well, it exists if you can find values of x, y, and z that satisfy both equations. Now, one of the interesting things about this is that they'll satisfy both equations, but these lines might pass through this point at different times. Right? To keep this in mind, I like to use a train analogy. Right? So trains running along train tracks. Imagine these two lines, the line L and the line K, represent train tracks. It's often the case that train tracks cross, but the trains do not collide because they pass through the crossing point at different times. So when we're trying to solve for these values x, y, and z, we don't really want to use the same parameter variable. It's a lot clearer, I think, to use a different parameter value for the second line. So instead of using t, I'll actually use s when we solve these equations. But in general, you'll have a setup like this. Here, I'm assuming the vector m has components m1, m2, m3. Point P has components p1, p2, p3. Slope vector n has components n1, n2, n3. And base point Q has components Q1, Q2, Q3. So you have three equations, and most of these are constants. T and S are variables. So two steps. First, use two of these equations to solve for the variables T and S. So maybe you'll use the first two to solve for those. But we need to check to make sure you pass through the same point. We want to make sure that x, y, and z are all equal for those values of t and s. So whatever you get for t and s, if you plug them into the last equation, right, these two may be equal and they may not. If you get the same z value, then they pass through the same point. If you get different values when checking the third equation, that means they go through different points. All right, let's do an example. So here's two equations of two lines, L of t and K of s. And first we'll want to write down some of the equations for the components. For the x of the line L, that's 2 times t plus 3. For the x of line K, that's 3 times s plus 2. That's our first equation. For the y component of L, it's 1 times t plus 4. For the y component of k, that's 2 times s plus 2. All right, so we'll start by working with these two equations. And it's probably easiest to solve the second equation for t, since there's no coefficient of t here, or coefficient 1. So you solve that for t, you'll find that t equals 2 times s minus 2. Right, solve for one equation, or sorry, solve for one variable in terms of the other. So now we can plug that in to the x equation, right, where we see 2 times t plus 3, right, that is 2 times this quantity, 2s minus 2, plus 3 equals 3s plus 2. Do some simplification, distribute this through, combine like terms. Once you do the algebra, you'll find that s equals 3, and plugging that into this equation here, if you put s equals 3 in, we'll have 6 minus 2, you'll find that t equals 4. All right, so this is your possible time solutions. Now, we need to make sure that at these times, the two lines go through the same x and the same y and the same z. So we need to plug these values into the z equations. The z component of L is negative 1 times t plus 5. The z component of k is 4 times s minus 11. All right, so the question, this is a question mark, the question is, are these equal for these parameter values? So plug t equals 4 in for t, plug s equals 3 in for s. Once you simplify both sides, hey, 1 equals 1. That is true, so yes, the lines intersect. If you got two different numbers, that means they pass through different z's, and no, the lines do not intersect. So to find the actual point, you could plug, say, the t value into the equation L, and you'll find that L of 4 is equal to 1181. And there's a nice easy way to check your work here. You can plug the other parameter value into the other equation, and you should get the same point. And so here, k of 3 equals 1181. So hey, we got the same point. And so these two lines both pass through this point. The lines do intersect. And again, the lines don't intersect if when you plug into the third equation, if you got two numbers that weren't equal. That would mean they don't intersect. Excellent. Now, again, even if they don't intersect, you can still keep doing math. In this case, we'd like to find the distance between two lines that do not intersect. Now, in order to understand this, the calculation actually isn't very hard, but it's important to understand why it works. When you measure the distance between two things, you're really measuring the shortest distance between those two objects. When we talked about a point and a line, the distance from the point to the line is the length of this perpendicular segment. It's going to be the same idea. To measure the distance between two lines, we want to measure the distance of a perpendicular segment between them. And this is kind of tricky. How do you find something perpendicular to both lines? And that might trigger a memory of a previous video. A perpendicular to two different things, you can calculate that using the cross product. All right, so the cross product is kind of the key here. To calculate the cross product of these two slope vectors, m and n, right, we'll call that cross product the vector d, and this vector, when it passes through these two when this cross product vector passes through these two lines, it's going to be perpendicular to both. And again, I know the picture doesn't look like it's really perpendicular, and that's the difficulty with trying to draw three-dimensional diagrams. So once you have this perpendicular vector, what we really need is this length between the two lines along this vector. Right, so if you started with the base points P and Q, you could calculate the vector v between P and Q, but the length of this vector is not the answer to the problem, but it kind of gets you a step in the right direction. Imagine taking this vector v and projecting it onto the cross product. Right, then this point kind of project down to here, this point will project to here, and the length of the projection is the distance between the two lines. That's what we're interested in. But the length of the projection, that also has another name, that's the component of this vector along this direction. So the component actually gives us the distance between these two lines. That's what we need to calculate. Right, so let's go ahead and do an example of this calculation. Right, let's say we have these two lines, L and K, and let's assume that we've shown that they do not intersect. The odds are, given two random lines in three-dimensional space, they usually don't. So let's say we have these lines with the slope vectors and these points. Really, we need to calculate a couple of vectors. First, the vector between the base points, the vector from P to Q. Calculate that as Q minus P. And here we'll get the vector 2 to negative 1. To calculate the cross product, it's okay to review your notes or look at the original video, but in brief, we use determinant notation to remember this formula. So a 3 by 3 grid. The first row are the standard basis vectors I, j, and k. The second row is the first vector. We're cross-producting the first slope vector. The third row is that second slope vector. And then the process is to extract 2 by 2 grids of numbers. The grid corresponding to the I component. Ignore the numbers in the I column. The remaining numbers form that grid. The j component. Ignore the numbers in the j column. The remaining numbers form that grid. For the k component, ignore the numbers in the k column. The remaining numbers form that grid. And don't forget your alternating signs, right? The j component has an extra negative in front of it. And then you calculate these determinants here by doing the formula A times D minus C times B. We do that for each of these 2 by 2 grids. Don't forget that negative. So for the first component, we have negative 1 times 1 minus 3 times 2. So negative 1 minus 6, it's negative 7. Second component is 1 times 1 minus 4, or 1 times 1 minus 2 times 2. So that's 1 minus 4. It's negative 3, but don't forget that negative sign. Turns into positive 3. The last component is 1 times 3 minus 2 times negative 1. And so 3 minus a negative 2, that gives you 5. Once you have this vector and then the cross product, that perpendicular, we're going to project or find the component of v along d. Formula is v dot d divided by the length of d. So we do some more standard vector calculations. In this case, it turns out to be negative 13 over the square root of 83. But in this case, that just means that the vector v and the vector d are pointing in opposite directions. Since we're interested in a distance, distances are positive, we can just do the absolute value of this. So the distance between these two lines, right, as measured along that perpendicular, is 13 divided by the square root of 83. And that's how that kind of calculation works. Oh, we can do a lot of stuff with points and lines. Right? I particularly like this topic because it really brings together everything you've learned up to this point. Right? Everything from the vector between 2 points, the lengths of a vector, the dot product of 2 vectors, components, projections, cross products. It all comes together in this topic. All right, it's been a long video, so thanks for watching.